Hello and welcome to Organic Chemistry 2. This semester I want to make sure that you all have some videos of what I would normally go over in class, which is going to consist of my notes, which you will sort of get used to instead of being in class. But the advantage of doing the videos is that you can actually watch these and pause them or fast forward if you are so inclined to do such. You can feel free to look back at these as you complete your homework prior to class. And these notes will be available for you on some different resources, so you can actually have a look at that. Okay, so to begin with Lesson 1, this should be somewhat of a review, but as we look at benzene, benzene can be drawn as two different forms of a resonance structure in both these positions. So you can think of the electrons being localized between two carbons here or here. But these are two different resonance structures, and they simply aren't the reality of what we find in benzene. Instead, what we see more like is the hybrid version of those two resonance structures, whereby electrons are delocalized, or otherwise they're no longer confined between those two particular carbons and are instead shared throughout the center of the benzene ring. You can look at any chemistry text and see what that sort of looks like on an electron density map. But basically, any of these three structures, when we write it as organic chemists, we really mean the same thing. So this is what closer to what benzene actually looks like, and these may not. When you look at resonance contributors, these give rise often to a hybrid form of a molecule. Hybrids can exist where electrons are delocalized or are not confined to a particular bond, but hybrids with delocalized electrons exist because they're lower in energy for the overall molecule. So what that actually means is that this structure is much more stable because it's lower in energy than are either of these. And that's simply why that hybrid exists. You can have other types of resonance structures that exist, but will not contribute as equally as others in an actual molecule. So here's what I mean by this. First of all, when you're drawing resonance structures, we can move electrons down to bonds, move bonds up to the next particular atom. Notice that our charge does not change between these two resonance structures. And the negative charge transfers from this oxygen up to this oxygen. That means that both resonance structures put a negative charge on an oxygen, and therefore they're relatively equal. So a hybrid form actually exists between these two. And you can consider this the hybrid of a carboxylate, which is the conjugate base of a carboxylic acid. If we look at an amide, on the other hand, this is a relatively stable compound. It's neutral. It's pretty happy. But you start moving electrons over and up, which gives you a valid resonance structure. Part of the reason why we know it's valid is that you've got a negative charge on an oxygen, positive charge on nitrogen. It can take that. Everybody has 8 electrons. Our octet is complete. Everybody's happy, except for the fact that you just put charges on atoms that really weren't charged previously. What that means is that this structure is much more likely to occur than this one. In other words, if you have a huge number of molecules, this is the form that a vast majority of them are going to be in. Or better yet, the equilibrium might shift so that you get like 1 or 2 like this for a second, and then it goes right back. Therefore, the behavior of this amide, though, may be slightly different in that the nitrogen might be slightly more positively charged, and you might get a partial negative charge on that oxygen that you simply wouldn't have if the nitrogen was a carbon instead. Or rather yet, any heteroatom that doesn't have electrons there. Okay. So just to remind you, if you have more resonance structures, to stabilize a particular charge or a particular molecule, period, then that's going to mean that the compound is much more stable. So when you're writing resonance structures, there's some basic rules that you should know. And these, again, are probably a review. But you can't change the location of the atoms. If you do, that becomes a conformer and not a resonance structure. All the sigma bonds have to remain the same and intact. So you can't start changing where the electrons are between atoms, because otherwise you get a different molecule as well. The octet rule still applies. You can't have 10 electrons around carbon, so no pentavalent carbons, okay? The total charge remains unchanged for a particular molecule. Just as we had with our carboxylate, the negative charge can transfer from one atom to the next, or one oxygen to the next, but the overall charge of this molecule is -1, and the same thing here. The overall charge here is 0, and if you add +1 and -1, it's also still 0. In other words, the number of electrons, or the electron count, does not change. You can only move pi or lone electrons, and they can only really move one step at a time. And what I mean by that is we can only move those electrons next door, either to, this is a particular bond, or in this case we're moving this bond up to a particular atom. These electrons cannot randomly go over here, at least unless there's a massive, well, there's a couple of exceptions, but you all won't see that in this class, okay? Okay, that's the end of lesson 1, and hope to see you in class soon. Thanks, bye.